Everyone. Today we're going to continue for chapter 6, which is the last major chapter for this class. So last couple of times we discussed hypothesis test, how to set up the hypothesis test and how to draw conclusion from the test. And we discussed one of the cases, which is large sample test for population mean. So today we continue section 6.3. Okay, this is the test for population proportion. Okay, so you will see the procedure is very similar to test for population mean. Just use different set of equations. Okay. So test for population proportions. Okay. For population proportions is a population mean for populations of 0 and 1s. So basically for Bernoulli population. Remember for Bernoulli population, for example, we toss a coin, we have two possible outcomes, head and tail. Okay, so if we define head as a success, 1, the tail will be 0, unsuccess. So we have 0, 1, so two possible outcomes. So here give another example, supply of semiconductor waffles claims that all the wafers no more than 10% are defective. Okay, hold on a second. Oh. Sorry, again, the right page. Okay. Section 6.3. All right, it's here. So if the population proportion of defective wafers are denoted by P, then the claim is that, oh, it's here. Sorry, it's here. So 10% are defective. A sample of 400 wafers are tested, and 50 of them, or 12.5%. Okay, because 50 over 400 is 12.5%, are found to be defective. Okay, so the question asks, can we conclude that the claim is false? Okay, so he claimed no more than 10% are defective. A sample of 400 wafers found 12.5% are defective. Okay, which is higher than 10%. But can we conclude that his claim is false? Okay. So our hypothesis test is similar to the one we saw before, like the large sample test for mean. Okay, but now we have a different sample which has success and failures. Okay, and for success we can define success as defective waffle, and for sample 400 waffle we have 12.5% are defective. So if we define the population proportion of defective waffles is P, okay, then the supplier claim is that the P is less than 10%, P less than 0.1. Okay, and then we get a sample of 400 waffles. Okay, so we try to draw some conclusion for the population proportion P based on the sample proportion, which is 12.5%. Okay. So if we define X is number of success for an independent Bernoulli trial, okay, and for each trial we have success probability of P, okay, and we know X will follow binomial NP. Okay, so this is based on what we learned from chapter 2. Okay, so binomial means we have n identical Bernoulli trial, and each trial has the same success probability P. So the null hypothesis H0 can be set up as P less than are equal to P0. Okay, so P0 is the value we want to check. Okay, in this example, it is 10%. Okay, or H0 can be set up as P large or equal to P0, or P equal to certain value P0. Okay, and another condition is NP and N times 1 minus P are greater than 10. Okay, so this is another condition. This is based on central limit theorem, okay, which we'll talk in a moment. Okay, so we calculate the z-score. The z-score equation is this. Okay, so this is sample proportion. Okay, in the example, it is 12.5%. Okay, and P0 is whatever the question want to check. In this example, is 10%. Okay, and sample size is n. Okay, so we calculate the z-score based on this equation, and then we calculate the p-value. Okay, so same procedure as we did for the test of large sample population mean. Okay, and then depending on how H1 is set up. Okay, so if H1 is set up as P larger than P0, then p-value is area, okay, to the right of Z. Okay, so if A0 is set up as P less than P0, okay, the p-value is area to the left of Z. Okay, like this. And if P not equal to P0, then it will be sum of two tails on the left and on the right. Okay, the sum of the areas in the two tails cut off by Z and minus Z. Okay, so this is basically the same as we did for large sample tests for population mean. Right. So the only difference is the equation for z-score. Okay, this equation are different. Right. Then go back to the example. Let's see how we can resolve this question. Right. First of all, always look at the last sentence. Okay, so can we conclude that the claim is false? Okay, so based on this, can we conclude we know this is chapter 6. Okay, we know this is a question about hypothesis test. Okay, then let's read the question and we can figure out this is question about proportion. Okay, so we have a sample of 400 waffles. 50 of them, or 12.5%, are defective. Okay, so we try to compare with P0, which is 10% here. All right, so first of all, let's set up H0 and H1. Okay, so as I mentioned before, whatever the question asked will be H1. Okay, so the question asks, can we conclude that the claim is false? Okay, claim is false. The claim is false will be H1. Okay, then let's look at what is the claim. So the claim is that all of the waffle no more than 10% are defective. Okay, so no more than 10% are defective is the claim. Then the claim is false means the p-value will be more than 10%, more than 0.1, right? Okay, then H0. So H0 will be opposite of H1. So P larger than 0.1 for H1, then H0 will be P less or equal to 0.1. Okay, and also remember the equality line always go to H0. So that's the two rules we set up H0 and H1. Okay. Okay. And then let's calculate the z-score based on the equation here. Okay. The z-score will be sample proportion minus P0. Okay. So the sample proportion will be 50 over 400 samples. So 12.5%, 0.125. Okay. So P0 will be 0.1, 0.1. Okay. And N is 400. Okay. So we can plug in this number into the equation of Z. We can calculate the z-score of 1.67. Okay. I will also talk about here why we need to calculate z-score as that. Okay, and as I said, this is based on central limit theory. Okay, so the node distribution, as we learned from central limit theorem, will follow a normal distribution, okay, with mean value of p and the variance of this. Okay, so this is based on central limit theorem. Check section 4.11. Okay, and that's the reason why we have a condition such as n times p and n times 1 minus p are greater than 10. Okay, because only under this condition, it will follow a normal distribution of this. Okay, and then the z-score is based on the node distribution of this. Okay, that's how we calculate the z-score. Okay, but of course you don't need to know the background information here. So what you need to know is you calculate the z-score based on this equation. Okay, and the z-score turned out to be 1.67. Okay, and then the next step is to calculate the p-value. Okay, so how to calculate the p-value? P-value depending on how H1 is set up. Okay, so in our case, H1 is P larger than 0.1. Okay, so which is the first case, P larger than P0. P0 is 0.1. Then P-value will be the area to the right of Z, to the right of Z. Okay, so how to find the P-value on the right of Z? Of course, we use table 8.2, the Z table. Okay, so it turned out for Z value of 1.67, the area to the right of Z, that's the p-value. P-value is 0.0475. Okay, so we compare p-value with the alpha. Okay, the question didn't tell us what alpha to use. So if no alpha is given, we use alpha of 5%. Okay, so compare p with 5%. So p less than 5%, 0.0475. So just barely less than 5%. Then we can draw the conclusion, okay, because p-value less than alpha, so we will reject H0, okay. Then H1 is true, so we can conclude H1 is true. You can just copy whatever H1. So H1 is whatever after can we conclude that. Okay, so the conclusion is, okay, so yes, we can conclude that the claim is false. Okay, the claim is false. All right. Okay, so that's the first question for today. Here is another example. Okay, so again, look at the last sentence. Can we conclude that? Okay, can we conclude means that's chapter 6 problem. Okay, that this method produce result within tolerance limit more than 17% of the 75% of the time. Okay, so 75%, this is a proportion. Okay, that's the proportion. Then let's read the question. An article presents a method for measuring isometric height above sea level. Okay, a sample of 1225 baselines. Okay, so 926 of them gave result that were within class C spirit leveling tolerance limit. Okay, so we don't need to know what does that mean. Okay, so that's the proportion. Out of a sample of 1225, 926 within a certain limit. Okay, so can we conclude that this method produces result within tolerance limit more than 75% of the time? Okay, so that's the hypothesis test for proportion. Okay, so we use the equation from this section here. Right, so let's set up H0 and H1. So the first step, H0 and H1. Okay, so H1 again will be whatever the question asks, whatever after can we conclude. So this will be H1. So this method produces result within limit more than 75% of the time. Okay, so P0 more than 75%. Okay, then H1, H0 will be the opposite, P0 less or equal to 0.75. Again, the equality line always go to H0. Okay. Second step, the sample proportion. So 926 out of 1225. So that is 0.7559. Okay, so a little bit higher than 75%. But can we conclude that based on this sample result? Okay, it is within the tolerance limit more than 75% of the time. Okay, so then we calculate the z-score based on the equation, sample proportion, P0. Okay. The sample proportion is 0.7559. Okay. So P0 is here, 0.75. So the number question wants us to check. So that is P0, 0.75. Okay. N is 1225. Okay, so the z-score 2.48. Okay, so now not a very high z-score. Okay, and then p-value. Okay, the p-value is depending on how H1 is set up. Okay. For H1, p larger than p0, okay, p-value will be the area to the right of z. To the right of z. That's the first case. Okay. So because in our case, that's p0 larger than 0.75, so the p-value will be the area to the right of z of 0.48. Okay, so that area is the p-value, which we found out from table 8.2. Okay, the p-value turned out to be 3.3156. Okay, so pretty large. Okay, so larger than the alpha of 0.05. Okay, because p-value is larger than 0.05, we cannot conclude H0 is false. Okay, so we cannot conclude H1 is true. So cannot conclude. Okay, H1 is true. Okay, and H1 is this method produce result within tolerance limit more than 75% of the time. So we cannot conclude that this method produce result within limit of more than 75% of the time. Okay, so that's the procedure to do hypothesis tests. Okay. Again, so p-value is 31%. Okay, larger than alpha of 5%. All right. So questions or comments so far? All right. So section 6.3, we just finished. That's the test for population proportion. Section 6.4 is small sample test for population mean. Okay. So also for chapter 5, if you remember, we also have confidence interval for small sample of population mean. Okay, let's read in what condition we usually use the equation here. Okay, so one condition, of course, is the sample is small. Okay, so remember when we have a large sample, okay, we can use sample standard deviation S to approximate the population standard deviation sigma, because the sample size is large. Okay, but when the sample size is small, we cannot use S to approximate sigma. Okay, when the sample size is small, we have actual condition, which is the population need to follow a normal distribution. Okay, this is the same case for confidence interval. When we have small sample, we have actual requirement for the population. It need to be follow a normal distribution. Okay, so same as chapter 5. So if it follow a normal distribution, then we can use the student's T distribution. Okay, right. And the last item here says the only time that we do not use student's T distribution for this situation means when the sample size is small, is when the population standard deviation sigma is known. Okay, so if the sigma is known, then we do not need to bother use student's T distribution. We just directly go ahead use normal distribution. We use the z-score instead of student's T distribution. Okay, so that's a condition. So under the special condition that the sigma is known, even though the sample size may be small, we still use Z table. Otherwise, when the sample size is small, we use T score. Okay, and the equation for that is here. All right, so the setup x1 to xn is a sample from normal population. Okay, again, that's the necessary condition where population sigma is unknown. Okay, if population sigma is known, then we use z-score. Okay, like I mentioned here. Then, depending on how H0 is set up, mu less or equal to, large or equal to, or equal to mu 0. So mu 0 is the value we want to check. We calculate the t-score based on this equation. This is sample mean, mu 0, sample standard deviation, and sample size n. Okay. Then, based on the t value, we calculate the p value, the p-score. Okay, so remember for students t distribution, t has degree of freedom. Okay, the degree of freedom is n-1 in this case. Okay, then depending on how h1 is set up, okay, if mu larger than mu 0, then the p-value is the area to the right of t, less than mu 0 to the left of t. Okay, so same as the z value. If it's not equal to, then will be two tails added together. Okay. Exactly the same as the previous cases. Example number 5. Okay. Again, look at last sentence. Can we conclude that? So that tells us that's chapter 6. Then this will be H1. Okay, the mean pH level is less than 7.0. Okay, what does that mean? Let's read the whole example. Before a substance can be deemed safe for lamp feeding, its chemical properties must be characterized. Sorry. Article report that in a sample of 6 replicates, so 6 sample size, small, okay, of sludge from a New Hampshire wastewater treatment plant, the mean pH level is 6.68. Okay, so this is about small sample population mean. Okay, so that's the hypothesis test for a small sample of population mean. All right. Again, the first step is to set up H0 and H1. Okay, so H1 is here. The mean pH is less than 7.0. Okay, so mu less than 7.0. Then H0 will be mu large or equal to 7.0. Okay. Then the next step is to calculate the t value based on the equation here. Okay. So the sample mean is 6.68. Mu 0 is 7.0. Sample standard deviation is 0.2. Square root of sample size 6. Okay. So the t value is this. Okay. So for t-value, we use table 8.3. Okay, and it based on two parameters. Okay, so the t-value and also the degree of freedom. Okay, the degree of freedom is n minus 1, which is 6 minus 1, that's 5 degree of freedom. Okay, so then look at table 8.3. We cannot find the exact p-value, okay, but we can find a range for a p-value. Okay. Okay. Because each one is set up as mu less than mu 0. Okay, so mu less than mu 0, then the p-value is the area to the left of t, to the left of t. Okay. So the t-value is found out to be minus 3.92. Okay, which is between a 2 t-value. Okay, so here is t-value of minus 3.9, sorry. Minus 4.032. Okay, and the other t-value here is minus 3.365. Okay, and the probability for this t-value of minus 4.032 is 0.005. And for t-value of minus 3.365, so that probability is 0.01. Okay, so that tells us for our t-value of minus 3.92, the p-value is between 0.005 and 0.01. Okay, but for t table, we cannot give the exact p-value. Okay, so we can see p-value is between 0.005 and 0.01. Okay, so which is less than 5%. So p-value less than alpha of 0.05. Okay, so then we can reject H0 and conclude H1 is true. Okay, so the answer is yes. Okay, we can conclude that the mean pH is less than 7.0. Or H1 is true. Okay. All right. So this is small sample test for population mean. Okay. We use students' t distribution when the sigma is unknown. Okay. The next situation is large sample test for difference between two means. Okay. In chapter 5, confidence interval, we also have confidence interval for large sample for the difference between two means. Okay, so same situation here. So if we want to know if two population mean are equal or not, okay, and then we're gonna get two samples, and for each two samples we have a sample mean value. If the difference between two sample mean is far away from 0, then we can conclude that the population mean are different. Okay. If the difference between the sample mean are closer to 0, then we may conclude that population mean might be same. Okay. So how to set up this? So we have two samples, x1, x2 to xn. Okay, and y1, y2, yn are large sample. Okay, with two different means, mu x, mu y, and two different standard deviation. Okay, and also require that these two samples are independent to each other. Okay, but that's no requirement for the population follow a normal distribution. Okay, so no matter what distribution follows. Okay, so no requirement for normal distribution because the sample size is large. And then set up H0. Okay, the difference between mu x and mu y less or equal to, okay, large or equal to delta 0. Okay, delta 0 normally is 0 if the question is asked if there's a difference between mu x and mu y. Okay, so typically delta 0 is equal to 0. Then we calculate the z-score. We use another equation for z-score. Okay. So in the case of sigma x and sigma y are unknown, then we can use sample standard deviation instead, because the sample size is big. Okay, so we can use S, X, and SY instead. Okay, so calculate the z-score, then calculate the p-value. Okay, same as before. Depending on how H1 is set up, so mu x minus mu y larger than delta 0, then p-value will be the area to the right of z. Okay, again, same as before. Less than left of z. Not equal, sum of two tails. Okay. Example number 6. Can we conclude? Chapter 6, question. The mean diameter of inclusion differs between the two shading glass. Okay, so the mean diameter differ or not. So that is difference between two means. So that is hypothesis test for difference between two means. Okay, and then let's say the sample size is large or small. A sample of 581, so large sample. Okay, so that tells us that we're going to use the equation from this section. Okay, section 6.5. Okay, so article compare property of welds made using carbon dioxide as shedding gas. Okay, so with those of welds made using a mixture of argon and carbon dioxide. So two types of shedding gas. Okay, one is carbon dioxide, another one is a mixture. Okay. So one property studied was the diameter of inclusions, okay, which are particles embedded in the webs. A sample of 544 inclusions using argon shedding gas, average of this much micrometer in diameter and standard deviation of this. Another sample, 581, using carbon dioxide shedding gas, have another average with another standard deviation. Okay, so that's the difference between two means. Again, the first step is set up H1 and H0. Okay, so again, whatever after the conclude will be H1. So that is H1. So the mean diameter of inclusion differ between the two shedding gas. Differ. Okay, so differ means mu x minus mu y not equal to 0. Okay, otherwise it will be equal to 0. Right? Then H0 will be the opposite. Mu x minus mu y equal to 0. Okay, so in our case, delta 0 is 0. Okay. Then the remaining will be simple. So one case, the mean standard deviation, sample size. Another mean standard deviation and sample size. Right. So the equation for z-score is here. Minus delta 0. Delta 0 is 0. Okay. Sample standard deviation, sample size for x and for y. Okay, so we can plug in this number into the equation of z. Okay, so z will be minus 1.97. 1.97. Okay. Then depending on how H1 is set up, so not equal to here. So the third case, mu x minus mu y not equal to 0. P-value will be sum of two tails. Sum of two tails. Here, one tail and the other tail. Okay. For z-value of minus 1.97, the sum of two tails will be 0.0488. Okay, just about 5%. Okay, so the p-value not about, just less than 5% alpha. Okay, so we can reject H0 and we can conclude H1 is true. You can just copy whatever H1 is. And of course, H1 is the mean diameter of inclusion differ between the two shedding gas. So we can conclude H1 is true. All right, so that's a large sample test for difference between two means. The next section will be our last section for today. Okay, so that's the difference between two proportions. Again, we have the same thing for confidence interval for chapter 5. So confidence interval for difference between two proportions. Okay, and we know for proportions, that two proportions follow binomial distribution. Okay. So the procedure for testing difference between two population is similar to procedure for testing the difference between two means. Okay, but here x and y follow binomial distribution. Okay, so if we want to check if H0 and H1 is set up as this one, okay, so H0 is Px minus Py large or equal to 0. H1 is Px minus Py less than 0. Okay, and we need to use sample proportion. Okay, this is the sample proportion for x and y. Okay. So based on the difference between the sample proportion, we draw the conclusion. Okay. We also must determine the node distribution. Okay. Okay. And based on central limit theorem, okay, when the sample size is large, then the sample proportion will follow a normal distribution. Oh. Let me rewrite the equation here. So Px minus Py will follow a normal distribution based on central limit theorem of is the mean value of Px minus Py with a variance of this. Okay. Okay. And we also need to get the mean value and the variance for this node distribution. For the node hypothesis, the H0 specified the mean value is 0. Okay, so that's easy. Px minus Py is equal to 0. Okay. Then let's find out the variance. Okay, to find out the variance, we need a so-called pooled proportion. Okay, so what is the pooled proportion? Okay, so the pooled proportion can be calculated based on the equation here. Okay, so the pooled proportion is obtained by dividing the total number of success in both samples, which is x plus y, divided by the total sample size, which is nx plus ny. Okay. Then the node distribution for the difference between Px and Py will be this. Okay, the mean value is 0. Okay, this is pooled proportion, which is calculated based on the equation here, and nx and ny. Okay, so finally, let's look at the setup for the hypothesis test for difference between two proportion. Sorry. All right, here. So x follow binomial nx, px, and y follow another binomial distribution ny and py. Okay, and this is the condition at least 10 success and at least 10 failures for each sample. Okay, and also they are independent to each other. Okay, H0 can be set up as this: Px minus Py less or equal to large or equal to 0. Okay, and this is sample proportion Px, Py. This is so-called pooled proportion. Pooled proportion. the equation for z-score is this, okay, as function of sample proportion and also pool proportion. Okay, all right. So after getting the z-score, we get p-value. Okay, the p-value is figured out exactly as before, depending on how H1 is set up. Larger than 0, p-value is to the right of z. Less than 0, left of z. Not equal to sum of two tails. Okay, again, exactly the same as before. Okay, so based on z-score, we calculate p-value and then compare p-value with alpha. Okay, same trick. That's the last example for today. Example number 7. Okay, so let's read it together. Again, look at last sentence. Can we conclude that? Okay. And this will be H1. So can we conclude that the proportion, okay, keywords, number 1, keyword number 2. So can we conclude that? Conclude tells us this is chapter 6 problems. Proportion means this is a test for proportion. So proportion of oil companies that employ method of risk transfer is less than proportion of construction company. Okay, so here talk about the difference between two proportions. And then we can zoom in the equation in this section, 6.6. Okay. Then let's read the remaining question. Industrial firms often employ method of risk transfer, okay, such as insurance or indemnity clause in contracts as technique of risk management. One article reported that result of a survey in which managers were asked which method have played a major role in risk management strategies of their firms. In one sample of 43 oil company, 22 indicate the risk transfer play a major role. Another sample of 93 construction companies, 55 of them report risk transfer play a major role. All right, okay. So set up H0 and H1. All right. So proportion of oil company employed a method of risk transfer is less than proportion of construction company. So that will be H1. So H1 will be Px minus Py large equal to 0, large or equal to, oh, sorry, that's not H1. So H1 will be Px minus Py less than 0. Okay, so if we define oil company as X and construction company as Y. Okay. So oil is X and X. Okay. So if oil company is X and construction will be Y, okay, then H1 will be Px minus Py less than 0. Okay. So oil company larger than less than construction company. Then H0 will be the opposite. Px minus Py large or equal to 0. Okay. Then let's figure out the parameters, nx, x, and the sample proportion px. Okay, so 22 over 43. and Y. So Y is a construction company. Y is 55. Sample proportion PY is 55 over 93. Okay. And also we have the pooled proportion. Okay. So plug in the number, the pooled proportion is 0.5662. Okay. The Z-score is here. Okay. Based on the Z-score equation, you plug in the number. Okay. So we calculated Z-score. Z-score is minus 0.87. Okay. We showed here. So because H1 is set up as less than 0, okay? For less than 0, which is the second case, so the p-value will be the area to the left of Z, left and Z. So that's why we get area on the left of Z, value of minus 0.87. So p-value turned out to be 0.1922, so very too big, okay? So larger than alpha of 0.05, okay? So the answer is no, we cannot conclude. We cannot conclude. You can just copy the last sentence here. We cannot conclude that the proportion of oil company employed method of risk transfer is less than proportion of construction company that too. Okay, or we see we cannot conclude H1 is true. Okay, because that's how we set up H as H1. Okay, so far we have discussed 3 or 4 many different situations, all about hypothesis test for large sample population mean, small sample population mean or proportion, or difference between two means, or difference between two proportions. So we have around 3 or 4 sections remaining for chapter 6. You continue for Thursday this week for section 6.7, which is small sample test for difference between two means. Okay, so let's stop here for today. All right, any questions, guys, before we call it a day? Okay, thank you. See you on Thursday then.